Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be introducing the topic of scatterplots. In particular, we're going to talk about what a scatterplot is and how to interpret the information that a scatterplot is telling us by finding a best fit equation for that information, and then analyzing the equation itself, the model that we get to really try to understand the information we're provided. We should first understand what a scatterplot is compared to other types of graphs we typically see. Now, a scatterplot, it's a standard graph. It's a graph we see where we plot points in the xy plane. So we're dealing with the x-axis and the y-axis, and it's a standard graph we're used to seeing. The only thing that's different about this type of graph as opposed to other graphs we tend to work with in algebra courses, for example, is that we're not graphing a continuous line. Instead, we're graphing data values. We're graphing individual coordinate points. These points are relationships between the x and the y variable. So you can see an example right here. We have a graph, it's not of a continuous line, but rather it's individual coordinate points. And these points represent the relationship between the x and the y coordinates. So here, we can see the x-axis represents temperature, and the y-axis represent sales for ice cream. Now, the temperature is the temperature outside, sales is in dollars for how much ice cream we sell. You can see that these individual points represent that for certain given temperatures, we make certain sales in ice cream. Instead of having a continuous line that describes all this, we have individual points. The way in which we get scatter plots are typically from real-world data. So for example, let's say we owned an ice cream shop or we sold ice cream, and we wanted to see, is there a relationship, or what is the relationship between the temperature outside and how much we make per ice cream sales. So each day, we would measure the temperature and how much we made that day. And we get these data values. That's really where things come from. They're what's called discrete data. They're individual points. They're not necessarily connected on a continuous line. So really what we have here with our scatter plot is that we're plotting a model of individual relationships between the two variables. On this day, this was the relationship. On this day, it was this. On this day, it was this. And we're trying to see what information this tells us. The problem here is, how do we describe this information? How do we work with this information? Because the thing is, it's discrete. It's all individual points. It's not like a continuous line that we have an equation for. So what should we do with this? Should we, I don't know, maybe connect all of the dots, and maybe this will tell us something? Well, not necessarily, because I don't know what that equation is, and that would be really difficult to figure out. So what other things could we do to approximate this data or represent this data? What we try to do with scatter plots is we want to fit an equation that best represents the data, okay? We're dealing with approximations here, and we're coming up with what are called best fit equations. The most common type you'll see is the line of best fit. The line of best fit is a linear model or a linear equation that approximates the trend in the data. It's not a line that connects all of the points. Rather, it's a line that best estimates and best describes the trend that you're seeing in the data. Let's jump back to the other page. To me, these points look like they're following a certain trend. As temperature is increasing outside, the sales of ice cream increases as well. So if I'm trying to describe the relationship I'm seeing here with an equation, these points seem to follow a line. Maybe a line, I don't know, let's say this line right here. Okay, I just drew that line. These points look fairly close to this line, don't they? We might say that this line is the line of best fit. It's the model that best describes the data, okay? A couple things you should know about the line of best fit. It's an approximation. It's an estimation. You're not going to have one line that passes through all of these points. The only way that would work is if all of the points were literally on a straight line. Very rarely happens in real-world scenarios. You have them scattered around. You have them dispersed around. So we come up with a line that kind of approximates the data, that best represents it. Think about how when we talked about finding averages for data, the average was kind of like the best approximate number or the most central number to represent the data. Similarly, the line of best fit is the line that best represents what's going on here. If you had to describe it with a straight line, we would use this one. Now, I drew this line of best fit. Some people might say, well, how do you know that's the line of best fit? What does best fit mean? What if I drew that line, or that line, or this one? They're all very similar. How do you know which one is the best? Well, we're going to define a best fit equation as an equation that minimizes the distance between the data points in the scatter plot and the graph of the equation. That's the most common way of defining best fit. What it's trying to do is minimize the distance between all of the data points that you have and the line you're trying to draw to approximate them. So if we look at this graph right here, we can see that for given points, there's a certain distance between the point and the line. Some of them are really close. Some it looks like even, some it even looks like the line passes through. But others, there's a little bit of distance in between. So we want the line that shortens the distance for all of the points. It's the minimum distance. I should let you know, because what we typically teach students is that the line of best fit is drawn by just eyeballing. I can't tell you how many times I hear students talk about the line of best fit as well. It's just the line that looks like it goes through the data. You kind of eyeball it and you draw it and yeah, it looks pretty good. That's the best fit. That's not really the way in which you determine the line of best fit. I just drew this line because I'm working on a tablet and I'm drawing. There is an equation for the line of best fit. There is an actual process. You learn about this in statistics. There's an actual process you use to determine the exact equation of best fit. The line of best fit, there's a very specific equation, or a process, I should say, that you do to come up with that. It's not just, what you eyeball and guess. There's a very specific way, and there's one line that will minimize all of these little distances, okay? So we don't have time to get into that. If you'd like to learn more about that, feel free to research the topic of linear regression and look up the formula for trend lines or lines of best fit, or feel free to come by my office hours or send me an email. I have my email posted at the end of the video. So that's how we're defining best fit. It's the line that minimizes all of those distances. So you can have a line of best fit that does this. You can also have other models that do this as well. It's common to sometimes have exponential models of best fit. You can use an exponential function to describe data that grows exponentially. You can even use quadratics. A quadratic is a degree 2 function, so something with x squared to it, and you can use a quadratic, which makes a parabola, to describe certain relationships as well. Heck, I've even been in a class where we used a circle of best fit. We actually created, for a given data set, we found the circle of best fit where we drew a circle that would minimize all the distances between the data points. That doesn't really happen that often. More so, you would use linear for straight lines, as well as exponential or quadratic at times to model data. Now, when you're working with these different types of models, you really need to keep in mind what the parent functions are, because that's going to tell you what the shape you're trying to get is. What I mean by that is, when you look at a scatter plot, you have to kind of say to yourself, well, is the data following a straight line? Is it a curved line? If it's curved, what way is it curved? Is it curved exponentially or is it curved quadratically? So we need to keep in mind what the general shapes of these functions are. So linear, that's easy. It's a straight line. Now, a lot of times students will forget you can have a straight line that's increasing. You can also have a straight line that's decreasing. So be on the lookout for that. You might have data that's decreasing over time. It's still linear, just going down as we move left to right. Then you have quadratics. Remember, quadratics form parabolas. Okay? Quadratics, things like x squared, anything with x squared, like degree 2, those are going to form parabolas. And again, you can have parabolas that open downwards as well. Okay? Parabolas, these U-shaped graphs, can open upwards, they can also open downwards. Same thing with exponentials. These are things like some number, let's say 2 to the x power. So some number to a variable exponent. And their graphs are like this, where they curve upward on one side. But you can also have what's called exponential decay, where the graph goes down really quickly, like this. So these are the general shapes that you're going to have. You really should understand these different shapes and the different shapes of the parent functions for other types of common functions. I do have a video posted on basic function types. You should go and watch that video to remind yourself about the different function types that you might see and what their graphs would look like. So these are the general graphs. We have straight lines, we have these U-shaped graphs, and then we also have these kind of half increasing graphs, I guess you could say, where one half goes up really high and the other half goes down really low. So these are the general models that we're going to want to fit to our data. Now, let's take some time to practice deciding if data fits a certain type of model. So in this problem, we need to find which of these four models, I should say which of these four scatter plots, should be modeled using the linear equation y equals ax plus b, where a is less than 0. So a couple things to point out there. We want to find which of these fits a linear model where a is less than 0. So notice that we have two qualifications to meet here. Well, hopefully we can use the process of elimination and say, well, we got to find a linear model. A here, does that U shape look like a straight line to you? Hopefully you're saying no. So we know immediately A is not going to be a linear model. Linear, straight line, that looks like a U. That looks like a parabola. So I'm going to say that's probably quadratic. So we're not going to do A. B kind of looks like a straight line. C kind of looks like a straight line. Okay. What about D? Well, it's not as straight as these two. It's a bit curved, isn't it? You know what? If I'm thinking back, problem D is reminding me a bit of the exponential. So I'm going to say D probably isn't linear. At least it's not as linear as B or C. So we're using the process of elimination to meet the first condition. Okay, now we have the things that we think are linear. Let's look at the second condition now. A is less than 0. A is less than 0. Well, we have this equation, y equals ax plus b. Does that look familiar to you? Y equals ax plus b. Where have we seen that before? Wait a minute. Isn't that the same thing as y equals mx plus b? We're just using a different letter? That's actually correct. We are using the exact same slope-intercept form here. These two equations are the same thing. We're just using a different letter. Instead of m, we're using a. That's a common thing you might see on tests like the SAT, where they try to change up the equation, but keeping the same format, okay? So here we realize we're dealing with a linear equation. That is the y-intercept. Let me move this down here. This then, the a, would be the slope. So what does it mean that a is less than 0? Well, hopefully you're saying that means a is negative. A is a negative number. So a here is some negative number. Well, how does that tell me anything about the two graphs here? Pause the video, take a minute. Think about what it means that a here is a negative number. Our slope, because that's what a is a negative number. What does that tell us about the graph that we should get? All right, well, hopefully you had some time to work through this. We're thinking about what does it mean that a is a negative number? What does it mean that our slope is negative? Well, that means our line will be decreasing. We're making a line because it's linear, and it needs to be decreasing because it's negative. So we're going down as we move from left to right. Which of these two graphs moves down as we go left to right? Well, it looks like C does. Because B, if I drew a line that moves down as we go left to right, that doesn't really fit that data, does it at all? Instead, it's moving up. So B would not work. Instead, we're going to say C should be our solution here. So C here is the scatter plot, which really should be modeled by the linear equation where the slope is negative. That's all that we're saying here, okay? I'm not putting it in words that, hey, the slope is negative. Instead, I'm telling you to think about what it means to be less than 0. I'm not exactly saying that the slope is negative. I'm telling you that the slope is less than 0. So I am saying it's negative, but I'm not saying it outright. This is a common type of wording that you might see on tests like the SAT. So you really want to be careful and think about what does it mean that this condition is here, a is less than 0. Well, what does that mean for my equation? What does that mean for my graph? Because we're talking about graphs here. What does that mean for the graph? What would it look like? How would it look different? So really take that time to think about that when you go ahead and make your decision. Again, use the process of elimination to help at least narrow your choices down, and then keep looking at the more specific conditions to help you find the correct answer. Let's take a look at another example where we have to fit a model to a specific data set. Here we have this scatter plot, and we're told that A, B, and C are constants. Remember, constants are numbers. They're standalone numbers. They're not variables. So we know that these 3 letters are going to represent numbers. We don't know what they are, but they're just, any numbers, like 2, 3, 4, whatever. And we have this condition, A is greater than 0. Okay, last problem, A was less than 0. Now it's greater than. That means it's a positive. Which of the following equations for the line of best is the line of best fit for the scatter plot? So which of these types of equations would best represent this data? Okay, I'm looking at this, and hopefully you're seeing too, there's a U shape here. U shape, well, let's see. We talked about linear, that's a straight line. Nah, this really doesn't fit a straight line. We talked about quadratic and exponential. In a quadratic, it made a U shape. It was a parabola. So I'm thinking that this is probably represented by a quadratic. That's what my thought is. Let's take a look at the examples that we have. Notice that these are all in general format. They're not like specific equations. So let's go through them one by one. The first one, y equals ax plus b. Well, we just worked through that. That's a linear equation. The next one, y equals a to the bx power. Notice that we have the variable in the exponent. That should give away that you are working with an exponential. And then these two, because they're both of x squared, these are both quadratic. Quadratic. So my initial guess is that because the graph looks like a U shape, I don't want to use a linear and I don't want to use an exponential. I must use one of these quadratics. So I use the process of elimination to narrow down my choices. Now let's get into more of the specifics. Okay, I know I'm dealing with one of these quadratics, but which one? Well, I know A, B, and C are just numbers, but I also am told that A is greater than 0. A is greater than 0. That means it's positive. Hopefully you remember back from our work with basic types of functions that when your leading coefficient on the first number here, when it's positive, your parabola opens upward. If it was negative, your parabola would open downward. Since we're opening upwards, I'm going to say number 4 is the correct solution here. This would be the equation or the format of the equation we would want for the line of best fit because it's quadratic and because it's opening upwards. That is kind of how we're going about thinking about determining what the model should be. You have to know that what's central to my understanding about how to solve these problems is me knowing what the functions look like. Me knowing that these are the general shapes for these functions is really central to me being able to do this. So it's important to keep that in mind and to go back through and, watch those old videos, do some research, and do some practice with different types of functions and understand generally what does the shape of the graph look like. We want to now work with a more specific equation that helps us determine what the model is. In this problem, we need to decide which of the given equations is the specific equation to this line of best fit. So instead of us deciding which type of equation, now we are told, okay, it's linear, it's a straight line here. Now we got to think which of these linear equations is the equation for this line. Well, why don't we think about it like this? Anytime students need to come up with a linear equation, I always tell them the only information you need to come up with is the slope m and the y-intercept b. Find the slope, find the y-intercept. If you know both of those, you know the equation of the line. So what I want you to do is pause the video for a minute, take some time, and I want you to think, how can you find the y-intercept and how can you find the slope of this line? Okay, in this problem, we're trying to find what is the slope and the y-intercept of this equation right here, this line of best fit. Well, you can see by the graph, it's pretty obvious what the y-intercept is, isn't it? We're crossing the y-axis here at the point 0, -1. So b, the y-intercept, should be -1. If I'm looking at these equations, I'm noticing that this one that had a +1 and this one that had a +1 for the y-intercept cannot be the solutions because their y-intercepts are positive. That would mean you cross the y-axis here. We don't. We cross it down here. So neither of these are the correct answer. So this first one and this fourth one both have the correct y-intercept. It's the slopes that are a little different. So let's think, how can we find the slope of this line? There's a couple ways of doing this. There's a couple ways to find the slope. You could say, well, I know one point, and it looks like I know another point. And maybe then I would be able to kind of say, well, it looks like I go up 1, 2, 3, and over 1. So it's probably close to a slope of 3. And of these, this is closest to 3. So I would probably say the last one, number 4, is the correct solution. But you can also think about it, instead of just looking at the graph and trying to manually compute what the slope is, work with the two slopes you're given. 0.4 is the same thing as 4/10, 4 over 10, or 2 over 5. 2.5 is the same thing as 2.5, or 5/2. So notice that, oh, look at that. They're basically reciprocals of each other. So you can decide now which of these is the more appropriate slope. Should you go from here up 1, 2 units and over 1, 2, 3, 4, 5? That's a slope of 2/5. Oh, that's not very steep. That's actually quite flat. No, I probably don't want that, that slope. But what about the slope of 5 over 2? We're going up 1, 2, 3, 4, 5, over 1, 2, roughly that. That's more close to what the slope of this line is than if we were all the way over here. So I'm going to say that this equation is the one that best represents the line of best fit. That equation is probably closest to what the equation for the line of best fit actually is. Now, as we're talking about how to analyze and how to think about lines of best fit, as far as which type of line would be best, would it be a straight line, a U-shaped line, a curved line, and then how we can interpret what the actual equation of that line is, one of the things that we also need to talk about is how is that line in relation to the data points? So we say we want the line of best fit to be the line that minimizes the distance between all the data points. And it's the line that we can best come up with to describe the data. Well, we have to also talk about how good of an approximation that is. So there's a couple things that we need to talk about when we talk about correlation. When we talk about correlation, we're talking about the relationship between the variables. When we say correlation, we're describing how related are the two variables. How good of a fit do we have with our model? That's really what correlation is talking about. What's the relationship? Is there a strong relationship or not? So we're mostly going to refer to this correlation in terms of linear. This is mostly going to be when we talk about straight lines, okay? Now, when you talk about correlation, you can have positive or negative. So positive correlation, let me write that in blue actually. Positive correlation is when the data increases left to right. So as you move across the graph from the left to the right, your data is increasing, generally speaking. A negative correlation is when the data decreases left to right. When the data decreases left to right. That's what a negative means. It's the same thing as slope, okay? When you talk about positive slope, you're referring to the graph increasing. When you talk about negative slope, you're referring to it decreasing. So that's just the idea of what positive and negative means. The phrasing I want to point out to you now is strong versus weak. Strong versus weak correlation. Strong correlation is when the data is very close to the line of best fit. That's the idea of a strong correlation. The data is tightly packed together. It's very close to the line of best fit that you have. A weak correlation, a weak one, is when the data is spread out. What I mean by that is the data isn't always that tightly packed around the trend line. Rather, it's spread out. There's bigger and bigger distances between the trend line and the data points. So let's take a look at an example here that describes the relationship between the number of sick days used by employees at some company A and the outside temperature. So this company was saying, does the number of sick days that an employee takes, is that related to the temperature outside? And they went through and they studied different examples. So these are the numbers of sick days used. And for each of those, this is the outside temperature for the day, the average outside temperature for the day. And you're trying to see, is there a relationship here between the x-axis variables and the y-axis variables? So we would say that there is really no relationship between the two variables. So there's no relationship between the number of sick days used at company A. So there's no relationship between the number of sick days used at company A and the outside temperature. There is no relationship here because we can't really fit any of our models to this. We could try to draw a straight line, but what do you think? If we drew that straight line, it would have a weak correlation. It would have a very weak correlation because it's all spread out. It's, I could draw this line, but it really doesn't model much. All of these points are too far away. They're too spread out. They're not really fitting a specific straight line trend or a specific U-shaped graph, okay? So this is another type of common question you might see where you have to describe the relationship that you're seeing between two quantities. You can describe that relationship as being weak. You can describe it as positive or negative, but just be sure you're clear with your descriptions of what's going on here. Make sure you understand how to tell if something's weak or how to tell if something's strong. Let me go back a couple examples. So when we take a look at this scatter plot here, we can see that all the data is very tightly packed around this line. They're all very, very close. They're not that far off. So we would say this is a strong correlation. The data fits the model quite accurately. While our other example, let's jump back again, while this model here really it's not that tightly packed around the trend line or the line of best fit. It really doesn't fit any type. So we would say there really isn't a relationship, and if we had to describe the correlation, the relationship between the variables, it's weak. So there's not really much we can say about the number of sick days people used and the temperature that it was outside. That's the idea of what it means to have a scatter plot and how to interpret a scatter plot using lines of best fit and understanding how to interpret those fit lines. If you have any questions or want to go over anything more together, feel free to let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know what you thought of the video, if you have any questions, and until next time, take care.